Our eyes are by far our most important sensory organ. I've read that something like 80% of our sensory information comes from our eyes, particularly information that protects us from danger, like walking into doors or television sets, or, for instance, and sometimes even having vision isn't enough. Turns out you actually have to pay attention sometimes. Man, my face still hurts. Anyway, these days, most of us engineers are busy building this internet of all kinds of things. We're connecting cars and drones and toothbrushes, and if we want those things to be truly smart, then they need to be able to see. Except maybe that toothbrush, because then that'd be kind of silly, right? But bear with me here. Hi, I'm Amelia Dalton, host of Chalk Talk. Embedded vision is one of the most challenging computational problems we grapple with these days. We need enormous computing power, lightning-fast latency, and oh yeah, we need to do it all on basically no power. My guest today is Aaron Behman from Xilinx, and we're going to talk about enabling embedded vision. Take a look. Get it? Because take a look. Anyway. Before we get started, don't forget to click that link. There you can find out more information about embedded vision solutions from Xilinx. Hi, Aaron. Thank you so much for joining me today.
Thanks, Amelia. How are you?
I'm great. So, to start off, let's talk about what exactly embedded vision means.
Well, it can mean a lot to a lot of different folks.
True.
Here at Xilinx, we've settled on 6 key driving applications that we see will shape the future of the electronics industry. In particular, the 6 applications that we're focused on, where we see a really great fit for our products, is in medical imaging, advanced driver's assistance, or automotive in general, because we're seeing a transition from just collision avoidance to semi-autonomous and even fully autonomous vehicles. So lots of great opportunities there.
Yeah.
Augmented reality, another very interesting area for us. Not so much on the consumer side, but really more on the industrial side.
Okay.
Yeah, in fact, it was today, I was reading about a power tool that's using augmented reality to help, if you can imagine like a jigsaw, help to cut precise measurements on wood. Yeah, so all sorts of interesting use cases. Certainly, we've seen a long-standing legacy in the area of industrial machine vision. So that's using embedded vision systems to help automate the manufacturing process. Vision-guided robotics and drones are another key area where we're seeing a lot of excitement and a lot of new design start activity. And then certainly surveillance has been another key area where we see a lot of opportunity for embedded vision, not just for traditional use cases like looking out for the bad guys, but also using really sophisticated algorithms to track people and their behaviors. So imagine for business intelligence purposes, using embedded vision in a surveillance use case within a store to understand what aisles maybe are getting less traffic than other aisles, so that the store can put on special offers and drive more traffic throughout the store.
Interesting. So what kind of growth opportunities are you seeing in embedded vision today?
Well, if you look at the markets that Xilinx is focused on serving today, we support the automotive industry, the industrial, scientific, and medical industries, which we summarize as ISM here internally, the aerospace and defense market, as well as the audio, video, broadcast, and consumer markets. We're seeing within the automotive space, as an example, embedded vision systems getting integrated into front camera systems to provide cars with the ability to see the road in front of them.
Yeah.
We're also seeing a lot of suppliers to the automotive OEMs, as well as the OEMs themselves, looking at interesting algorithms, in particular machine learning or deep learning, to give these systems the ability to make decisions autonomously. I can talk to you a bit more about that a little later. Also, surround view, so being able to stitch multiple image sensors together to create a cohesive and complete view of the vehicle.
Right.
Would be another example. That's actually an example of homogeneous sensor fusion. Driver and passenger monitoring, so understanding whether or not a driver is distracted or drowsy, about to fall asleep, and maybe the car should take over and drive them to the next rest stop.
Wow, cool.
Yeah, and then also in automotive, we're seeing augmented reality start to play a role in heads-up displays. So just an example on the automotive side, some of the examples or interesting areas where our customers are headed. On the industrial side, we're seeing augmented reality play a unique role in helping to make production lines more efficient by providing all of the production details and instructions directly to the user in a transparent headset that they might wear that might tell them how to assemble a new product or how to perform maintenance on a particular piece of machinery. We talked a bit about surveillance. Robotics is another interesting area. There's this notion of cobots, which are collaborative robots that will actually work alongside you and will be able to identify what you're doing and steer clear of your actions to help you be more efficient in the factory. Medical diagnostics. We continue to see amazing advancements in the medical field, and certainly providing better resolution and better insights will help detect early critical diseases and help medical providers treat those conditions.
Sure.
And then certainly within an industrial manufacturing context, using machine vision techniques to do inspection and detection and keep, again, factory lines running smoothly. In the other market segments that I described, the aerospace and defense or audio, video, broadcast, or consumer markets, again, a lot of interesting applications like using embedded vision for guidance systems, using cameras and displays for interesting consumer applications. Great example would be these 360-degree cameras, which we're starting to see emerge.
Sure, yeah.
These are these really great cameras that you can use to capture an entire environment and be able to share a much more immersive experience. Again, another example of using homogeneous sensor fusion to stitch together in a very seamless way in real time all of this image data to create a very immersive experience. And then virtual reality, augmented reality, and drones, as I mentioned, are other very interesting uses for our technology and some great applications.
Cool. So, Aaron, let's talk a little bit about the trends that we're seeing in the embedded vision space.
Well, number one is just ubiquity of embedded vision.
Sure, yeah.
We're not seeing it, or we're starting to see more and more cameras appear, not just in the stores that we shop in, the restaurants that we dine in, or even in our homes, but also in our vehicles. And a lot of these cameras are hidden to, again, help collect a lot of information and make decisions for us. Another area where we're seeing big emerging trend is making the cameras intelligent, right? So not just collecting the image data and passing it on to an individual or the cloud to do further processing, but actually doing real-time analytics at the edge and determining whether or not to take action.
Yeah.
And with that, we're seeing machine learning emerge as a very interesting and viable set of algorithms that can help make decisions at the edge.
Sure.
We're also seeing open frameworks. We're also seeing developers operate at a much higher level than I think we've traditionally seen and what we've traditionally served as a company. Examples of this would be individuals that are using C or C++ to write their vision algorithms and then being able to then target that directly to our hardware. We're seeing a lot of use of OpenCV and OpenVX, which are a set of vision-specific libraries.
Yeah.
Which help automate a lot of the rote kind of typical things that one might want to do when developing a vision processing pipeline. And then great emerging frameworks that help stitch all of that, or in other words, help you be a lot more productive, right? So you don't have to write as many lines of code.
Yes, everyone loves that.
Absolutely. And then security. Security is a very key concern, and certainly Xilinx is the only integrated solution with both a processing system and programmable logic, which really helps to prevent malicious users from going in and tampering with the device or even accessing sensitive information. So that's a big trend or a big care about that we're hearing in this industry.
Sure. So, Aaron, let's follow the money here. Where is Xilinx seeing success in embedded vision?
Well, as I had mentioned, advanced driver's assistance, or the automotive space, has been one area where we've seen a lot of traction. Now, we've been investing in this market for many, many years, and we're starting to see the fruits of that investment pay off. We'll see over 24 million units ship, which is a 3x increase in what we've seen in previous years.
Wow.
We'll see over 80 models ship. These are OEM models that will ship with Xilinx devices integrated into their advanced driver's assistance capabilities or features. So this is things like lane departure, drowsy driver detection, etc.
Okay.
New features that are just starting to come out from the auto manufacturers. Today, we serve and support over 200 companies in the embedded vision space.
Wow.
That number's growing very quickly. Mm-hmm. And based on some of our market research, we see this as an extremely fast-growing market. In terms of end revenue, it's about a $100 billion industry today. So that's if you add up the revenue from all of the cars that are shipping, all of the surveillance cameras. But that's going to grow by 2020 to $350 billion. Wow. So just huge, huge growth.
Huge, yes. So what do you think are the advantages from a platform position here?
Well, I think the best way to address that is to take a look at the Zinc class of SoCs. So that includes the Zinc 7000, all programmable SoC, and then, of course, our newly introduced Zinc UltraScale Plus MPSoC device family, which integrates an ARM-based processing subsystem along with other processing systems in the case of MPSoC, along with the programmable logic in the FPGA.
Right.
And from an embedded vision perspective, sensor fusion would be one key example. I've been talking about that, but what does that mean?
Yeah.
Sensor fusion can mean homogeneous sensor fusion, as I was describing in an ADAS use case, where you're stitching together multiple image sensors around a vehicle and trying to create a complete and cohesive view of the environment. Similarly, that 360-degree consumer camera does that as well.
Right.
But in some cases, those ADAS systems, for example, might want to also exploit heterogeneous sensor fusion, which means you're now layering in additional sensor types to bring in a whole new level of perception.
Gotcha. Okay.
So one example of that might be integrating thermal sensors into front-driving camera assemblies in vehicles to detect if there's a deer on the road, as an example, and then help the car make a decision to halt operation or move to a safe spot. So a unique ability that Xilinx has is you're really only limited to the number of sensors you want to integrate and fuse together by the amount of I/O that we offer in our devices.
Okay.
And so if you look at the Zinc family, the Zinc 7000 family, we have very small, low-end devices where you could get upwards of 4 camera sensors integrated into a single device, to very large devices where you could get tens of image sensors integrated to do some very sophisticated image signal processing.
Cool.
Yeah, absolutely. And then in addition to that, being able to then negotiate between all of these connectivity standards that are coming into the device. In some cases, you'll be bringing in image data right off of the sensors. So the ability through programmability support the latest and greatest image sensor interfaces like MIPI or more traditional interfaces like LVDS. Also, you've got varying types of output interfaces like GigiVision, CoExpress, CameraLink, USB 3, all of which are germane to industrial use cases, to more consumer grade or broadcast quality interfaces. So Xilinx has put a lot of focus and energy into bringing to market all of these connectivity standards, being able to, through intellectual property, instantiate those standards. So any-to-any connectivity becomes another key aspect that really makes us unique. And then that, along with the processing system in Zinc, allows for real-time vision analytics. And again, the key there is real-time.
Right.
And being able to do that at the edge. So using Zinc to identify the objects, do that heavy lifting in the fabric, and then being able to assign the metadata within processing subsystem is a key area.
All right, Aaron, let's talk about the biggest strengths Xilinx is doing in embedded vision system development.
Okay, great. Yeah, let's actually sum up some of the things we've already discussed.
Perfect.
So certainly one key strength that we have, as I was just describing, is our strength in being able to do real-time image recognition and analytics. And that's not just at low resolution, but at very, very high resolution, very high frame rate. I love what the entertainment industry refers to, the technical industry, like SMPTE, for example, in terms of the trends. It's all about more, better, and faster pixels, right? Mm-hmm. So True. More pixels going from HD to full HD to 4K to 8K, better pixels going to deeper color depths, high dynamic range that provides even better ways of perceiving the environment, to faster pixels, which is speeding up the frame rate so that you can get rid of motion blur. And from a Hollywood action film, sure, I get that. That's important. You want to make it look as crisp as possible.
Right.
But from a device that's going into your vehicle that's going to save your life, absolutely having that ability to do that at very high frame rates in real time is life critical. Sure. So that's an example of one area where we certainly shine in this space. All programmable platform reuse, because as a company, we offer a wide breadth of devices. Our customers can design an initial product, and then they can create low-end or high-end derivatives very easily.
Nice.
They can also look to extend their brand into other markets by adding in new features in a very seamless way. Scalable sensor fusion, we've talked a lot about how important that is and the strength that we have in being able to support numerous channels of vision processing pipelines. And then from a lot of the benchmarks that we've been doing, Xilinx continues to prove to be one of the best solutions in terms of the highest performance per watt. And really the industry's only single chip security and safety device is another strength that we have.
All right, Aaron, let's put this into the real world. Give me some examples of embedded vision that you're seeing every day, real world stuff.
All right, absolutely. I think a perfect example, it's getting a lot of attention right now, are vision-guided robotics and drones.
Yes, drones. Yes.
Yeah, everybody wants one if they don't already have one or they want another one. But
right.
Let's maybe back up a bit and at a very high level, let's look at the overall system architecture of a drone. It's an extremely complex system comprised of three primary subsystems. The first, of course, would be real-time motor control, right? You've got to control those props at very precise RPMs to make sure that you can control the drone in a very precise way. Software-defined radio is another very critical subsystem. And then, of course, precise embedded vision. So using sensor fusion and a number of the other things that we've talked about to perceive the world around you.
Right.
Let's talk about maybe some of the differentiating advantages that I mentioned and how those apply to drones. So very high frame rate, critical. When you've got a drone moving at a very fast rate, it can't make decisions off vision artifacts that appear because the frame rates just aren't high enough.
Right.
And so that's critical for recognition and analytics. We enable that obviously through massive parallelism. Just the nature of our devices allowed you to take very big bandwidth heavy operations and cut them down into smaller chunks and then process them all at once.
Sure.
The ability to support very large sensor payloads on these drones. So not just integrating maybe 4 or 6 or 8 camera sensors around the drone, but also leveraging things like LiDAR and thermal imaging.
Right, yeah.
To provide even greater perception is critical. It's really the most computationally productive platform that's enabling the highest performance per watt. And what I mean by that is a drone today, typically you can get 15, 20 minutes of use, and you need to really focus on having very power efficient electronics on board. And if you're trying to do very sophisticated operations like sensor fusion in traditional processors that exist, you're going to eat up a lot of power.
Sure, yeah.
Heat actually is less of a concern in drones because they've got onboard air conditioning with the propellers, but just throwing that out there. And certainly all programmable platform reuse would be another example where you can target an initial product and then create higher end variants or lower end variants. And we're seeing that happen already with a lot of companies that are in this space.
All right, Aaron. So my favorite drone application is terrorizing my cat, but I'm guessing there are other less mean and less frivolous applications for drones out there.
You're a mean person.
Well, I can be.
I might do the same thing. No, just kidding. Certainly there are. And as I was describing, there are just an amazing amount of very creative applications for all of embedded vision. But looking at drones specifically, we're seeing use in certainly the entertainment and media world.
Sure.
It used to be very expensive to rent a chopper for the day to do some skyline aerial shots.
Right.
You've now got independent folks or folks that are producing content on YouTube that can do that with very low cost equipment now. So that's a great way to democratize that. Certainly doing inspection on equipment in certain areas where it's just not safe, or it's just not practical to send a team would be one area. We're seeing the emergence of commercial drones being used in agricultural use cases. I don't know if you've seen this great Audi commercial that's kind of a takeoff on the birds.
Oh, yes, I have.
Yeah.
Yes.
Really great commercial where it's portraying basically the equivalent of an Amazon delivering packages and just going haywire. So another example would be retail, where you're using drones to deliver goods on demand to consumers. Also using drones to survey very large areas and get new insights. So there are companies that are actually using drone technology to survey stockpiles of raw materials. And they're now able to do that a lot faster. They can do it in a matter of 20, 30 minutes versus what would otherwise take a day. And the measurements that they're getting are a lot more precise, which means that those companies are able to order less of those raw materials. And then law enforcement would be another obvious area where we're starting to see drones take off.
Okay, so besides drones, even though I love me some drones, what are some of the other hot trends you're seeing in embedded vision right now?
Well, within embedded vision and also within drones, we're seeing certainly a need to integrate multi-camera vision, provide a complete perspective with surround view, also introduce a diverse sensor modalities to produce enhanced perception. So the discussion we had a bit earlier around integrating thermal sensors to spot that deer from afar on the road would be another example of heterogeneous sensor fusion. And then the processing performance can now support very dense implementation. So Xilinx enables developers to implement many more processing pipelines than they would have maybe considered before.
Sure.
There are other computer vision techniques that are being integrated into drones and embedded vision at large, like SLAM, which would be for simultaneous localization and mapping of an environment.
Okay.
So actually in real time forming a map of an environment so that a robot or a drone knows specifically where to go.
Very cool.
Optical flow, another example. So understanding the delta in terms of motion between frames to understand where an object is moving, and then being able to overlay on that predictive analytics around where an object may be heading.
Cool.
And then a lot of traditional techniques like pattern recognition and object recognition.
Sure.
But probably the hottest topic right now that's certainly getting a lot of excitement, and we're all talking about it a lot here at Xilinx around the water cooler, is machine learning techniques that are building on traditional techniques that were used in computer vision. These techniques promise much better recognition capability. So imagine if you're an algorithm developer, you might traditionally have to go in and identify this is what a car looks like, or this is what a person looks like.
Right.
These algorithms, which are based off of artificial intelligence techniques and blend between the disciplines of computer vision and neuroscience, are actually replicating our brains in a way to actually learn themselves and make those inferences themselves, which is really, really exciting. And that helps with things like object detection and classification through techniques like neural networks. This includes convolutional, deep, and recursive neural networks.
All right, Aaron, can you explain to me the machine learning dichotomy?
Well, yeah, sure. I mean, what we mean by a dichotomy is when you're developing a machine learning algorithm, you actually have to train the algorithm initially. And from a compute perspective, there's a very specific type of processor that you need to use to do that. You really need to make sure that you're leveraging very precise compute units. And it's through training that the model, as I said, is formed. There are many different approaches: convolutional neural networks, deep neural networks, recursive neural networks. These are all very interesting techniques. And it tends to be, when you're training an algorithm, a relatively lower volume application. And I would liken it to a high performance compute application.
Okay.
That's really what you're doing. And it leverages and really needs double precision floating point unit math to be able to build these models. So really not a great fit for Xilinx because of the nature of our architecture, but really something that's best suited for general purpose graphics processing units.
Okay.
If you take a look at once that model's been defined and you're going to go off and deploy it in a vehicle, in a drone, in a vision-guided robotic that's going to help an elderly person live a life at home longer than they might have before.
Yeah.
You're going to need super efficient processing, and it really doesn't need the same level of precision that you would need in what you might use to train the algorithm, right?
Oh, okay.
So think about, you really have to study hard when you're learning something, but once you're off book and you understand a concept, you don't need to be as precise, right?
Sure.
So, and this, of course, has a huge potential in terms of volume. So automotive, vision-guided robotics, drones, surveillance, medical imaging, these are all applications that from an inference, when you're trying to infer what the object is around you,
right,
you just need fixed point math to deploy those models. So really FPGAs, but even more so integrated FPGA-based SoCs are an ideal target for these sorts of applications.
Yeah, that totally makes sense. But Aaron, let's step back. We're getting a little deep here. How is this put all together?
Well, I think the best way to make sense of all of this is to start by examining what a traditional image processing pipeline looks like.
Okay.
So on the left, we've got an image sensor that's sensing the environment around that. And that could be replaced with a non-visible light sensor like IR or UV. And we've got to interface that sensor from the outside world into the digital domain, connect that up to the FPGA.
Sure.
And so we use a number of connectivity standards like LVDS or MIPI to interface those. Certainly Xilinx offers that, but our ecosystem does as well. And then you've got to do some sort of pre-processing on all of that raw data. You've got to debayer it, which is a technique that's used to extract the right colors from the image data. The image data doesn't necessarily capture RGB, red, green, blue data as our eyes might. And so there's a bit of conversion or pre-processing that needs to happen there.
Sure.
In a lot of cases, you need to convert the color space from RGB to YCRCB. You need to maybe scale the image down to a particular region of interest that you want to go off and analyze. And then from there, you're going into upstream processing techniques, computer vision and machine learning techniques. So libraries like OpenCV and OpenVX, or deep learning or optical flow or SLAM or stereo vision, these are all techniques that would be implemented in the programmable logic portion of the device. And then once you've analyzed all of that information, munged it, processed it, done what you need to do with it, you then need to get it out of the device onto the next stage. It could be to another subsystem that's going to make a decision to take action, or it might just need to go out to be visualized or monitored somewhere. And so you'll use output interfaces like HDMI, GigiVision, CoExpress, CameraLink, USB 3, and SDI as predominant standards that one might use in a vision system.
Okay, Aaron, Xilinx can't be the only company at this embedded vision party. Who else is attending, and what are they bringing?
Really good point. I mean, we need to make sure that we focus on certain key attributes like bringing to market world-class silicon and tools and frameworks. And so we address this market through a very rich ecosystem of partners that we've worked very hard to curate over the last several years. And so if you look at this diagram here, this is very closely aligned to the processing pipeline that we just discussed. And you can see there are a number of companies that we work with that provide connectivity solutions, that provide specific video processing or image processing algorithms, emerging companies that are working in the deep learning or neural network space. So really it's through this collection of companies that together we're able to address the embedded vision market and help our customers develop just amazing products at record speed.
Excellent. This was super cool, Aaron. Thank you so much for joining me. I really enjoyed this Jock Talk.
Same here. Thanks a lot, Amelia, and I'll talk to you soon.
And before we go, don't forget to click that link. There you can find out more information about embedded vision solutions from Xilinx. For Chalk Talk, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out the on-demand section of EE Journal or head on over to YouTube, keyword EE Journal.